It was discovered by Galileo, refined by Isaac Newton, and in the hands of Albert Einstein, provided a theory of the mechanics of the cosmos. It was one of the deepest mysteries in all of physics. All bodies fall with the same constant acceleration.
In a vacuum, all bodies fall with the same constant acceleration. That's it. That's the law of falling bodies. It doesn't seem like much to get excited about. And yet, just look at what it says. First of all, it says that the effect of gravity on all bodies is the same, regardless of their weight. From Galileo to Isaac Newton, right down to Albert Einstein, that's been one of the central mysteries in all of physics. Furthermore, it says that bodies fall with constant acceleration. And finally, profound and important though all this is, it violates our simplest intuition because it happens only in a vacuum, not in the world we're familiar with.
To make any sense at all about how and why bodies fall, we need to separate the effect of gravity on a falling body from the opposing effect of the air through which the body is falling. In other words, we have to imagine a body falling, not through the air, but through a vacuum. For instance, what happens if a penny and feather drop simultaneously from the same height? They behave exactly as we'd expect, each falling at a very different rate than the other. But that's only because of the effect of air resistance on the two objects. In a vacuum, a penny, a feather, and any other object will fall at exactly the same rate. With virtually no air remaining inside the glass tube, the penny and feather are now in a vacuum. When the penny and feather are released, we'll witness the law of falling bodies in action. Without the effect of air resistance, in other words, in a vacuum, all bodies, regardless of their weight, will fall at exactly the same rate. Galileo couldn't produce a vacuum, but he could imagine one. He pictured a heavy body attached to a lighter one. Would this compound body, he asked, fall faster or slower than the heavy body alone? If the lighter body did fall more slowly, it should slow down the heavy body. So the compound body should fall more slowly than the heavy body alone. But the compound body is actually heavier than the heavy body alone. Therefore, the compound body should fall faster than the heavy body, not slower. Obviously, the long-held view that the heavier a body is, the faster it falls, leads to an inescapable contradiction. Galileo realized that the only logically acceptable view was that all bodies, regardless of their weight, fall at exactly the same rate once the effect of air resistance is removed. We do know one thing about the rate of a falling body. The speed of the falling body increases as it falls, which means that it accelerates, dropping faster and faster as it falls. If this is 1 unit of distance, this should be 3. This should be 5, and so on, which is exactly what they are. Galileo was right. In successive intervals of time, the distances fallen do follow the odd numbers. But there's something else going on here that Galileo understood perfectly. Notice the total distance fallen at each point. After the first time interval, 1 unit of distance. After the second interval, 4 units of distance. After the third interval, 9 units. After the fourth, 16 units. In other words, at the end of each interval, the total distance fallen is 1, 4, 9, 16, 25, and so on. And those numbers, of course, are the perfect squares. So the distance fallen is proportional to the square of time. The law is, all bodies fall with the same constant acceleration. Acceleration is the rate of change of speed, and speed is the rate of change of distance. So we have, in fact, 3 precise mathematical statements of the law of falling bodies.